All right, let's get started. This is a tutorial for R code for chapters 11 and 12. So if you go under week 9 on Canvas, you'll see code for chapters 11 and 12. Go ahead and download both of these two files. Again, this is our file. This is our dataset file. So once you download, open R, and let's open the R file that you just downloaded. And let's start with chapter 11. Chapter 11, we looked at normal distribution, right? And how to standardize normal distribution to a standard normal with mean 0 and standard deviation of 1. So, and we learned how to compute z-scores. And so let's look at an example using R. So we looked at in class this example, woman's height follow normal distribution is 64.5 inches and 2.5 inches as its standard deviation. What percent of women are shorter than 67 inches tall? To compute that, R uses this command p-norm. So this p will give stands for cumulative probability. So anything to the left of this normal curve that you specify here will be computed. The area under this normal curve to the left of this Q value will be computed. And that's exactly what we are looking for in this problem. We are looking for probability of your X less than 67. So this will give you that probability. And you have to specify the correct mean and its standard deviation of X. And then this R will automatically compute z-score and then compute the area under the curve that you're looking for. Or you could also do this after standardizing. If you standardize this data, 67 minus 64.5, whole thing over 2.5. If you do that, you get z-score of what? Z-score of 1. And you can also compute the area under this z curve. This z-score has mean 0 and standard deviation 1, so you can specify that. And if you, the p norm will give you any the area under the curve to the left of this value z-score. So let's see what they return. So you can see that 84% is the answer. And if you do this one, again, this also gives 84%. So there are, you can do this either way. So that's chapter 11, how to use R code. That's R code for computing z-score and area under the curve. Okay, so, and then we also looked at in chapter 11, how to draw a normal quantile plot. What that is that normal quantile plot is needed before you make any inference about your population using normal distribution. You need to check if your data actually follows a normal distribution. So we are going to use normal quantile plot to check if your data follows a normal distribution. So in this line right here, I'm going to generate randomly 100 sample from a normal distribution with mean 0 and standard deviation of 1. So this is the sample from a normal distribution. R here denotes random, and norm here denotes normal distribution, and n is the sample size, mean 0, standard deviation 1. So I get 100 random sample from the normal distribution, and I'm going to assign it and call it Y, right? And then I'm going to use QQ norm plot, which is quantile to quantile plot using normal distribution. So that's what it means. And I'm going to plot Y on it. So then this will return a plot against plotting Y against a normal distribution. So let's go ahead and do that. I run the first line. You see now Y has been generated. There are 100 elements in Y. And run the next line. Then I get this normal quantile plot. So it looks like it is a pretty straight pattern. So let's draw this QQ line. This line will give you a straight line that if your data is normal, it should follow this straight line. So go ahead and run that line. Now I can see there is a line going through in the middle, straight line. And if your data set closely follows the straight line, we've said that your data is normal. And it looks like in this case, our data follows normal because it's following the straight pattern. And we expect that because our data has been generated from the normal distribution. So we know this Y is normal. This Y variable follows a normal distribution because we generated from Y, and we compute it against the QQ norm. If we plot it against another normal plot, it's going to give you a straight line. So this, we can see that Y is normal, and then when you plot it using QQ norm and QQ line, it shows a straight line pattern, and we conclude that they're both normal. The Y is normal. All right, so let's look at another example. This time, let's load this data set called the visitor data. We know how to load data set now. I'm going to call this visitor data. I'm going to assign it. And what am I going to assign to visitor data? Read.csv. So this is a CSV, comma separated value file. And make sure where you have downloaded the data set, go ahead and open properties, and I can see mine is at users, young, download. So let's go ahead. So let's run that. I can see my visitor data is right here. Number of visitors per day is our variable, and you see a counts variable here in the column. So let's go ahead and draw this data set. Using a QQ norm, I'm going to draw this column of this data set. I'm going to per day. Yeah. If you put a visitor data, just go through this. If you do visitor data $, it's going to give you the column inside it. And we only have one column, one variable inside. So I'm going to use that variable. If you press enter, it's going to autocomplete for you. Same thing at the bottom. In QQ line, you use visitor data and do $, it's going to ask you what variable you want to use. You want to use number of visitors per day. So press enter. Let's go ahead and draw them. Now you can see that this plot does not follow a normal. This visitor data does not follow a normal distribution because we see that the data set is away from this straight line. So this does not follow the straight pattern against this normal quantile. So we conclude that this visitor data does not follow normal distribution, and hence we cannot use normal distribution to make inference about its population. Okay. All right, so let's go ahead and move to chapter 12. In chapter 12, we learned some discrete probability distribution. And one example was a binomial distribution. Let's go ahead and take a look at the example. We looked at the color blindness example. Let's say color blindness in some population is about 8%. And we take n equals to 125 samples. So what is the probability that exactly one individual is colorblind? We know the binomial distribution, we can represent X, you can use X, this to represent this binomial distribution. And this probability of X equal 1 represents your X is your random variable. So how many of the colorblind person will you get out of this 125 sample? And we're specifying only one. So what is the probability of you observing exactly one individual who is colorblind when you take 125 samples out of the population, where the population has 8% chance of being colorblind? So if you do D binom, as you can see, this binom again stands for binomial. And this D is going to give you an exact probability at a specified point. So we want an exact probability at X equals 1, right? So we put X equals 1 here, and we put our size, which is n equal to 125, and we need to specify the probability of the color blindness, which is 0.08. And so if you run this line, it'll give you 0.0003, which means there is there's 0.03% chance of you getting exactly one colorblind person if you sample 125 from the population. So it's a very low probability. All right, and let's go ahead and look at the second example. What is the probability that 6 individuals or fewer in the sample are colorblind? So this one is asking what's the probability that you get 6 or less? So it cumulative up to X equals 6. So this represents what? Probability of X0 plus the probability of X1, probability of X2, added up to probability of X equals 6. So in this case, this binom again denotes binomial, and P we've seen before when we were doing normal example. P represents anything, area under the curve, to the left of what you specify here. So we want everything to the left of X equals 6, right? So you specify Q equals 6, which means this P binom function will take any area, will sum up all the area to the left of this 6. So Q equals 6, and then N equals, again, the size equals 125, probability equals 0.08. If you run it, you'll get about 12%. Okay, so we also looked at how you can use normal approximation to find out the same probability. So how do you do that? You have to check this condition, n times p is greater than 10, n times 1 minus p is greater than 10. We have np equal to 10 and n times 1 minus p greater than 10. So let's go ahead and use this approximation. All right, so this p norm, again, this norm is normal. P is to the left of this value, everything to the left, area under to the left of this value will be summed up. So specify the mean, which is 10, n times p, and standard deviation, which you got from n times p times 1 minus p all over square root. And if you run that line, it's going to give you about 9%. And that was without continuity correction. We learned that because probability, this binomial distribution is a discrete probability, and whereas this normal probability is continuous probability, we need to make a continuity correction for better estimation. So how do you make a continuity correction? You have 6, so the interval would go from 5.5 to the 6.5 for the continuous case, but we are looking at the case where we are adding up to the left of the this value. So we specified we want everything to left of 6.5. So this P norm, Q equals 6.5, mean and standard deviation, same as above. If you run it, you'll get about 12%. So this is more accurate than without the continuity correction. Right, we also learned another distribution, Poisson distribution, in chapter 12. This, we looked at the number of deer crossings per night is about 5, and lambda equals 5. What is the probability that exactly one deer cross on there's one deer crossing on a given night? So again, this D will give you exact probability, and this Poisson stands for Poisson distribution. So we want the probability of exactly one deer. So X equals 1, and you need to specify how many deer crossings per night, which is the rate of occurrence, which is 5. What is the probability that the fewer than 3 deer would cross on a given night? Again, this is looking for probability less than, equal to, less than 3. So this is equal to probability of 0 plus probability 1 plus probability of X equal 2. Right? So we have P, which is cumulative up to this point, which is 2, and this point is again Poisson. So I'll give you the probability. So if you run that line, what is the probability of X equal exactly 1? There's only one deer crossing. It's only about 3%. And if you run this, what is the probability of fewer than 3 deer crossing? Is about 12%. Okay. All right, I think this should be enough, everything you need to do homework for. So thank you for going through the tutorials.